We will now assume that a consumer's tastes satisfy the rationality assumptions, completeness and transitivity, as well as the monotonicity, convexity, and continuity assumptions. Monotonicity says more is better, or at least as good. Convexity says if you're indifferent between two bundles, then averages are better or at least as good as the extremes. And continuity says that there are no sudden jumps in your tastes. We will then begin with one bundle and ask where must all the indifferent bundles lie. And in the process, we'll construct what we'll call an indifference curve that contains that initial bundle. We'll again consider bundles that contain pants and shirts and start with some initial bundle A. This bundle A contains 8 shirts and 4 pants. The monotonicity assumption implies that bundle A must be better than all bundles that contain both fewer shirts and fewer pants. That implies that bundle A is better than all the shaded bundles. The monotonicity assumption also implies that bundle A must be worse than any bundle that contains both more shirts and more pants. Thus bundle A must be worse than all the magenta shaded bundles. If we are now to look for bundles that the consumer considers just as good as bundle A, in other words no better and no worse, we therefore can't look in these shaded areas. Instead, we have to look into the non-shaded areas and find such bundles there. We will do that in panel B of the graph. The continuity assumption implies that there must be some such indifferent bundles in these non-shaded areas, because as we remove some shirts and add some pants, there must be some point at which we reach a bundle where the consumer is in fact indifferent between that bundle and bundle A. Let's suppose that bundle B is in fact such a bundle. In other words, the consumer is indifferent between bundle A and bundle B. The bundle B that we've chosen contains 2 shirts and 8 pants. We can now construct bundle C as the average of the bundles A and B. On the shirts axis, we take the 8 shirts from bundle A, add them to the 2 shirts from bundle B and divide by 2 to get 5. On the pants axis, we take the 4 pants from bundle A, add them to the 8 pants from bundle B to get 12 and divide by 2 to get 6 for bundle C. Notice again that bundle C is the midpoint of the line that connects A and B. That's the strict average of bundles A and B. We could similarly have taken a weighted average, which would also lie on a line connecting A and B, but either further to A or further towards B, depending on how we weight the average. Whether we construct bundle C as a weighted average or as a strict average as we've done here, the convexity assumption now tells us that bundle C must be at least as good as bundles A and B. This is because the convexity assumption says that averages between indifferent bundles must be at least as good as the extremes, whether those averages are strict averages or weighted averages. We'll therefore assume that bundle C is better than bundles A and B and go from there. If bundle C is indeed better than bundles A and B, we can now imagine slowly taking away some shirts and pants in very small increments as we move to the southwest in the graph. As we do this, we're slowly decreasing the person's happiness relative to bundle C due to the monotonicity assumption. And if there are indeed no sudden jumps in the person's tastes, it must be that as we do this in small increments, we'll at some point reach a bundle F that the consumer considers just as good as bundles A and B. So if C is better than A and B, we know that by the continuity assumption and the monotonicity assumption, we can find this bundle F that's just as good as bundle A and B. We can imagine finding lots of bundle Fs by moving in different directions to the southwest from bundle C, and we can imagine doing it again from other bundles C that are weighted averages between A and B rather than the strict average between A and B. As we do this, we're plotting out all the bundles that the consumer is indifferent between relative to bundle A. In other words, we've just plotted out the indifference curve for this consumer relative to bundle A. This represents all the bundles for the consumer that are just as good as bundle A. Note that we've extended the indifference curve above bundle A as well as below bundle B, which we could do by simply picking other indifferent points that lie in the non-shaded areas and going through the same exercise as we've done here. Thus we've derived a general shape for the indifference curve, given the assumption of convexity and monotonicity. If the consumer is indifferent between all the bundles that lie on the indifference curve, then any bundle that contains more of everything relative to some bundle on the indifference curve must be strictly better. Thus all the shaded bundles that lie above the indifference curve are strictly preferred by this consumer to any bundle that lies on the indifference curve. We can therefore conclude that indifference curves representing tastes for consumers whose tastes satisfy the 5 basic assumptions we've outlined must take a shape that bends towards the origin. It could bend more towards the origin than the one we've graphed here, or less. It could even be a straight line if bundle C were just as good as bundles A and B rather than strictly better. We can also make one final observation. The shaded set of bundles that are strictly preferred to bundle A, together with the indifference curve that goes through bundle A, is known as what's called the upper contour set. This upper contour set of bundles that are at least as good as bundle A must be what we will call a convex set. A convex set is a set of bundles or a set of points such that you can take any 2 points in the set and the line that connects them also is fully contained within that set. You can now see why it is that we call the averages are better than extremes assumption a convexity assumption. The name convexity derives from the fact that the upper contour set of indifference curves from convex tastes are themselves convex sets.